So you had something like X, right, belonging to, let's say, a set of this one P labels, right? I mean, which is a positive examples. Then the idea is that your W transpose X, right, should be such that you want this to be kind of right greater than or equal to 0, right? And if it is if X belongs to negative examples, then ideally, right, you want this to be less than 0. Right, and the idea was that, I mean, you kind of update it, right? So in such a manner that when this condition is not satisfied, that means W transpose X is actually less than 0, then you make this update, right? You say that W new is equal to, let's say, W old, whatever you had, plus X, right? And for the other case, right? And so the idea is that, right, I mean, you get kind of effectively W transpose X plus X transpose X. And since you apply this condition only when W transpose X is less than 0, that means you want to kind of boost up that value, right? So that boosting happens right through this X transpose X, which is actually greater than or equal to 0. Similarly, when you have negative examples and you have actually greater than or equal to 0, that is when you apply the update rule. You make it W minus X, and which means that it becomes W transpose X minus X transpose X, which means that, right, you pull that number down, right? It's already greater than or equal to 0. You want it to be less than 0, so you try to kind of pull it down effectively by taking W transpose, I mean, W to be equal to W minus X. So that the W new transpose X, right, becomes W transpose X minus X transpose X. X transpose X is always a number greater than or equal to 0, and therefore, right, you pull it down, okay? And then, right, eventual idea is that you get to a point where, which then means that your cos alpha being equal to W transpose X by norm W into norm X, right? So the idea being that your W transpose X should eventually come out to be such that so if your W transpose X goes up, then which basically means that your cos alpha is going up. That means alpha is coming down. So you sort of end up making acute angles with respect to the positive examples, and then obtuse angles with respect to the negative examples, right? That's the idea. And of course the convergence proof and all, right, is really beyond the scope of this. Okay, now the universal approximation theorem, right, which we stated last time. So what it is saying is, so it's like saying that, if I had examples X, right, and I have to actually, right, build a network such that I arrive at some, let's say, right, G of X, whose analytical form I do not know, because if it was analytical, then it would be far more easy to solve that problem, right? But the idea is that you don't have an analytical solution, but you're kind of looking for this one mapping that will take you from X to some ideal G of X. And through the network, right, you're arriving some, there is a guarantee that through the network, right, you can arrive at, I mean, all that we stated last time, that you have now this one HL, right, hidden layer, which right, if it contains sufficient number of neurons with whatever activations, then you should be able to approximate G such that mod G of X minus F of X, right, this is, let's say, less than a small positive quantity, let's say epsilon for all X, right? This is what the right, universal approximation theorem says, but then it doesn't say as to how many neurons you need and all that. It just says that as long as you have a sufficient number, we should be able to approximate, right? I mean, it doesn't say what, right? I mean, it doesn't give a representation. It doesn't tell what is the best way to achieve this, right? Which is the reason why, for example, right, if you find out deep networks, right, the very reason why we call them as deep is because they have several layers stacked, right, one after the other. And actually the actual implementation happens through that and not really through one sort of a hidden layer, right, and that could have, I don't know, right, millions of neurons or something. So really what happens is, right, eventually people figured out that the way to actually achieve this, because the theorem per se does not say how to get there, right? And that has happened over years by, let's say, right, people figuring out how to do this. Okay, that I'll just, right, come to that in a moment. But before that, right, let's just look at then what would be a structure of that kind of a network, right? So what this means is that I have inputs, let's say x1, x2, right, all the way up to, let's say, xn. Okay, so this is my input, right, that goes to my network, and I have this one hidden layer. Okay, according to UAT, of course, we are still at the UAT point. We are not looking at a deep network in that sense, but we are looking at a network, right, a neural network that can achieve the task at hand. And what we are saying is, right, we got, let's say, right, several of these neurons sitting here, and each one of them is fully connected, right? I mean, that's the whole idea. So each neuron will get all the past inputs from all the kind of, right, previous, in this case, all the right inputs. So if you look at the first neuron, right, it will get from here. It will also get from here, and then right all the way here, and then each one will have a weight, right. So the weight is needed because sometimes, right, some of those inputs, okay, may not maybe totally irrelevant to the output, right. See, for example, right, you can kind of think of examples where, let's say, one of the inputs is not even, right, it doesn't even matter as to what value it takes with respect to the output, right. So that weighting is really for that. So this network should figure out along the way as to which ones really matter, right. For example, you could have something like an output, right, could be the right, a rating of a, let's say, right, a movie, and then the input could be actor, a director, whatever, right, and then it could be that could be that, right, one of those inputs could be simply, right, rain or something, right, weather. How does that matter, right, with respect to movie. So this weighting is really happening so that you can actually, so that the network figures out, right, which ones really matter for us to be able to get to the output that we want. And the same thing would also happen, let's say, with respect to the other neurons, right. So you again have to do a connection from here, and then the direction, of course, I'm not showing, but it's obvious, right. It's a kind of, it's called a feed forward network, right. So you are kind of feeding forward all the information, and then what happens, then you have, let's say, an output layer. Again, output, right, does not have to be a single valued, right. So this f of x or this g of x for that matter, right, it could also be, a vector valued function, okay, which is why I said, right, I did not explicitly mention that, but then it can also be vector valued. So really what you can have is something like this, right. So you have an output layer. So this is your input layer, let's call this IPL, let's call this HL, right, hidden layer, and let's call this the output layer. Okay, and again the output layer, so each of these neurons here will get an input from all of the right, previous previous outputs. So which then means that this guy would connect to this guy would connect to this all the way, this guy would connect to this, and then maybe, right, what will also happen is this guy will get inputs from all of them, right, and so on, right. And you can imagine that the right number of unknowns that you really have to solve for can really blow up, right, rather fast. For example, right, think of something like, if you have an input, right, which is let's say of a certain size, right. If you have, let's say, m, right, m cross 1, right, if that is the right, this one vector that's going in, and let's say I've got some, say, n cross 1 neurons, right, n number of, right, neurons, and where, let's say, n is far greater than m, typically, right, that would be the case. And let's say my final layer, which is the output layer, let's say I got some, like, let's say, right, p cross 1. Then you can imagine that in going from the input layer to HL, right, hidden layer, you're already looking at how many weights. How many weights do you have there that you have to actually calculate? That is m into n, right, m into n number of weights, and then the biases will be n number of bias terms, right, because each neuron will have a bias. So from going from here to here, right, you're looking at m into n weights plus n number of these biases, right, because each neuron you also have to find a theta, right, for each one of them, theta 1, theta 2, whatever, right, or right up to theta n. So you have that, and then in going from here to here, right, you're looking at what is that, n into p number of weights, right, and plus biases for the output neurons, which is like p, right. So now, given, if you have these numbers as large, which is right, typically the case, right, then you're looking at really learning. That's why when you kind of look at these deep networks, right, they end up you end up trying to solve for so many unknowns. That's because there's just so many weights out there, right, which you have to find out. There's so many bias terms, and so on, right. And that's also the reason why, let's say, right, when you handle images, right, this kind of an architecture is no longer the best, because an image typically is like 512 by 512, and actually there is a spatial correlation and all. Therefore, it's not a great idea to just stack it up as one single vector, right, what is called a lexicographical ordering. So you can just unwrap an image and put it as one long vector, but that's not the way it is done, because then you don't capture. Well, you can expect the network to capture all that, but that's not the way it is done, right. And you want some locality and all that. That's why you have what is called a convolutional neural network, right, which comes later. Now, this kind of this kind of an architecture, right, is called fully connected, FC, right, fully connected. There is also something called a fully convolutional network. So that is typically called FCN. So one should not confuse that and this. So when I say FC, this means fully connected. Okay. And here is your output, by the way, right, y1, y2, all the way up to, let's say, yp. Sorry, here, yp. Okay. Now, so number of weights and biases, right, is done. Now, then why then, right, one could ask, in fact, right, in the last class, even after the class, some people are asking, then why do you then do a deep network, right? So why don't you just solve a problem like this, right? Why don't you just have one sort of hidden layer and try to compute all those weights and biases? Now, this is this sort of rate, now this is in a sense empirical, and some of it is also because of the way that, right, one needs to have some kind of, attractability, right. I mean, attractability in the sense that when you train a network, you should also know, right, which way to head, because it's never very clear as to, how to kind of do this. And you also want some sort of right, explainability, in the sense that you should be able to associate things that are happening, right, inside the network to things that you really want to happen. See, for example, right, I mean, just as inside a human system, we have this idea that that, let's say, right, there are kind of, right, low level features, right, which we initially gather, then maybe, right, they kind of and then there's a pooling of those features in order to arrive at a certain higher level of features. Then there is probably another level of, some sort of a pooling that happens, which kind of brings those features together into a further whatever, right, whatever you mid level and then high level, and then okay, then there is then you get some interpretations. Now, similar to that, right, I mean, here also we want so right, over the years, what has happened is, right, people have actually figured out that that something like that, right, helps you actually achieve exactly the same task, but at the same time, right. So the reasons, right, I'll just write down, and most of them would be obvious, but I think it's just good to know as to why we actually, So instead of this, what is typically done is, in an implementation, right, what you would typically do is the following, right. So you will have let's say x1 to xn. What is it? xm. Sorry. Okay. So this should be m. So x1 to xm, okay, is what you have, and then what you have is typically a bunch of layers, right. I mean, sometimes these number of layers could go up to 50, 100 and so on. It depends, it can beyond a point, right, it can be intractable also, but yeah, but then typically, right, after a certain number of layers you may not even find any advantage. But it's interesting that, I mean, I was in a talk, right, that in one of the CVPRs, and there was this guy who works in actually brains. Then I was asked to give an invited talk, right, and he said that that actually none of these architectures really mimics what the brain does. Okay, so even though we tend to think that this is like the human visual system and all, but he says the human visual system does not do a back propagation and all that. And when the way we solve, let me see. One thing is that you can actually have an architecture that you think is more is tractable, is a kind of convenient thing to handle. But at the same time, you should also know how to train it and so on, right? Now, people have figured out how to train it and so on, but then he says that that's not the way, and nobody knows. Okay, by the way, he himself does not know how but then he knows for sure that this is not the way that things work inside our own system. Maybe true, right? Because very unlikely that right, we would do something like this. But anyway, right? I mean, given that whatever has happened, right, in this manner, one can, right, or some of you might still want to think about, is this the best way to do it, right? I mean, nobody is saying that this is the way to solve this problem, but this is the way it has been solved, right, along the way. And I think, right, we are just trying to sort of, right, interpret what has been done. Right? We are not trying to say that right, this is the best way to do things. So what is done is, right, so you have one layer, two layer. Okay, yeah, I already wrote down, right. So you got multiple layers, and then comes your output layer, right. What is that? Y1 to Y2 up to Yp, right. Now, so the idea is that, right, I mean, you might want to sort of, right, come up, and so that's the way this is done. And because of this, right, anything more than 3 or 4 layers, right, you would call it deep. Okay, and a deep network, right. So really, right, this is what we mean by a deep network, and this does exactly the same task, right, that you want. In the sense that irrespective of, you can think of the problem that you're trying to solve itself could be a regression problem. For example, you're going from an image to an image or something like that, or it could also be like, you're doing a classification problem where, let's say, right, given an input image, you want to say, right, to what class, right, from what class that image comes, whatever be it, right. Effectively, a deep network is trying to solve, right, I mean, either a regression problem or a classification problem, right. These are the two main problems that, let's say, right, people deal with. And and the reason, right, for actually for sort of going from sort of transitioning from here to this is for the following reasons, right. I'm just going to write down. Okay, so I'll just write down. So it gives a compositional feature abstraction, feature abstraction, right, which basically means that, see, for example, I mean, if I call this as let's say, right, I mean, something that is actually emulating some F1 sort of a functionality, and then let's say this is the second guy F2, and then so on, right. Now, what really is happening, suppose I call the input as some vector x, right? Then what is happening is after the first layer, right, you have let's say f1 of x, right? And then f1 of x becomes the input for f2, and therefore f2 acts on say f1 of x, right? And then you might have an f3 that is acting on f2 of f1 of x, right? So you've got like f3 acting on f2 acting on, right, f1 acting on x, right? So you have this kind of a compositional abstraction, right, which is actually going on, and the idea is that this compositionality is somewhat mimicking a human system, in the sense that, like I said, right, like I've said right, several times earlier also, that this sort of gives you, mimics the behavior of a human system, but again to a certain point, okay, and each one tries to figure it out in their own ways, which architecture works the best for a particular problem, okay. But I'm saying this is just a general what do you call, right, a general sense for how these things work, okay. So compositional feature abstraction is this one, just as in the human visual system, as in HVS, which is human visual system. Human visual system. Then, okay, now UAT itself, right, does not, UAT itself, right, limits itself, okay, so, right, I mean, itself does not say how easy it is to learn, right? Does not say how easy it is to learn this, how easy it is to learn this is a representation, or learn the mapping, right? It just says that, well, you can do it, right? But then it doesn't say whether you're doing it with just one sort of hidden layer, is that the best way to achieve it, or should we have multiple number of layers, right, effectively achieving the same thing, but then, right, which one is easy to learn is not clear, right? Then it does not even say, right, right, anything about that. And the fact is that people have found that, solving this, there are say efficient ways of actually doing it, okay. And or right, it also right, has and then it does not say how many neurons are needed, does not say how many neurons are needed, right? So it only says that a representation is possible, representation of any g of x, you can approximate it by some say f of x as close as possible, right? Doesn't say how many neurons you need for that task, how many neurons you need. And by the way, right, so this output layer that you have, okay, doesn't always mean that, right, you need a nonlinear activation there, right? All this nonlinear activation is all about this, okay. In fact, what to say, and even in the earlier example, right, where I think we did some OR or something we did, right. So even there, I chose an activation at the output, right, but then you can show that, right, it is not even, okay, you don't really need that, I mean, okay. So, I mean, you can have other ways of doing it also. So, and the other thing is, right, depending upon whether you are solving a classification problem or whether you are solving a regression problem, right, this output layer could have an activation function, could turn out to be totally linear and so on, right, because again, I mean, you need a bunch of values that you want to work with, right. It does not have to be a probability, right, all the time, okay. So therefore what you have in the output layer as activation depends, but all of this this hidden layer thing, right, so the activation is all for that, okay. It does not explicitly say that you need something at the output, you need nonlinear activations there. Then yeah,
so in these neural networks, the outputs each of y1 to yp can take only two values.
Each of y1 to y2 can only take two values. No, it's not like that. It depends upon what kind of an activation function you have. See, for example, if you have a step activation, right, like the one, okay, which we had, then of course, okay, then you have some, like, either it can take a 0 or 1, it just fires that way. But if you had something like a let's say sigmoid, right, it does not have to be, yeah, it can take no, it is real values. In fact, if you have ReLU, right, it can take, it doesn't have to be limited to anything between 0 and 1. Right, I mean, a ReLU, okay, right, would look like that. I mean, so it's totally linear after 0, so it can take any value. So that's why, right, I'm saying we are not limiting ourselves to what is happening in y, right. What you put in y depends upon what task you want to solve. Okay. Then there is one more thing, right, that you want to say, abstraction, then layered representation of features. So from simple to complex, right. So you can also, so this compositional feature is one aspect of it, and then you can also think of it as some kind of a layered representation, right, layered in the sense that okay, layered in the sense that, right, you right, typically believe that these features will go from being simple to complex. Okay, so that is simple to complex, right. So that means the initial layers would be would be learning some simple features, and then as you go further right down the network, right, I mean, what has been found is that, typically that's where the complex features, end up being. And that's also the way our own kind of, right, visual system works. So it's like taking simple things which you can easily identify, and then try to then go for more complex features. And what has also been, and then the other thing is, right, explainability. Okay, explainability, because that is kind of very important, right, because if you just do something, right, and then you're not able to explain why it works, right, it's not good. Right? I mean, it's not enough if you simply show that I'm able to meet my target. Right? I have built a network which can solve the problem, but then you have no insights into why that is going on. That's why you have what I call these ablation studies and all. Right? I mean, so right, somebody wants to know what happens if this is not there. What happens if that term is not there? What happens if this layer is not there? Right? If you remove it, why do you really need it there, and so on. So therefore, this explainability, right, is again very important. I mean, otherwise you are just solving something like a black box, right? And therefore explainability matters. And then the other thing, right, that is more of an empirical evidence is that you in fact end up using fewer neurons than a single layer. Okay, I mean, this again, okay, this is all empirical evidence, right? I mean, again, if you want, I mean, you should probably go and further read about these things, but what has been typically found is you need fewer neurons as compared to a single layer, Okay, so instead of having just one sort of hidden layer, what has been found is in fact you end up using fewer number of neurons. Okay, if you have a deeper network. So this is again empirical evidence. Okay, there is no kind of a theoretical guarantee or anything, just an empirical evidence. Okay. Yeah. So right, which is the reason why when you see these networks, right, they actually end up being what they are. Okay, like deep networks. Now, the two main tasks, right, which one looks at is what is called a regression task and what is called a classification task. Okay, the regression examples are many. For example, right, I mean, okay, now let me just. It does not have to be just right image based, even though this course is about images and so on. So regression, one example of image could be like I have an image which is, let's say, noisy, right, and I want an image, right, which is actually clean. I want an image to come out that I want a network which should take this and then, right, sort of suppress the noise and then it give me. You can't say remove the noise, right? That's not a good thing to say because you can never remove noise, but you can maybe suppress the noise, right, and get out an image which looks far more clean. Right? That's like a regression problem. And similarly, you can have several examples. But even in 1D, right? I mean, if you want to talk about, because right now we are still talking. And okay, one more thing, right? That right before I forget to say, right? So such a thing is called an MLP, which is a what is it called? MLP? Multilayer perceptron, right? MLP, multilayer perceptron. So right, you have all heard about this. This is called an MLP, right? Multilayer, right? It's like, right, multiple layers of a network, right? So you call it a multi-layer sort of a perceptron. And when you talk about convolutional neural networks, they are called CNNs and so on, right? So those don't have this kind of right, this kind of fully connected sort of a behavior. Okay. So from now on, whenever we say MLP, this is what we mean. Okay. So the idea is that right. Let me just go back to